We're going to simplify, expand, and condense logarithms, and in order to do that, we need to know some of our properties. So we've got log base a of u plus log base a of v. Both logarithmic terms have the same base. This is going to allow us to combine the two terms into one term in which we multiply the arguments. So u times v. It's called our product rule. So that's the product rule of logarithms. Then we have our quotient rule. Our quotient rule says we've got two logarithmic expressions in which they have the same base, so we're going to be able to combine that to be one logarithm with that base a, and then positive logarithms, their arguments go in the numerator, and negative logarithms, their arguments go in the denominator, and that's called the quotient rule. And I like to put the argument in parentheses. It's called the quotient rule. Then we have the power rule. When we have log base a of u raised to the nth power, that n that's in the exponent becomes a coefficient of the logarithm. So n times log base a of u. And that is the power rule of logarithms. And then here we have our basic definition of logarithms. This is exponential form. If I were to work on getting this out of exponential form, I would find that a raised to log base a of u is just equal to the argument of u. Now, sometimes students will cross off, like things cancel out. Nothing cancels out. Let me explain how this works. I have a base. I'm raising it to an exponent, log base a, so that base a is raised to a logarithm with the same base of u. And I'm not sure what that is, so I'm going to call it x for right now. I'm going to rewrite this in log form. So I'm going to write this in log form. When I write this in log form, I write log base a, so this base becomes the base of the logarithm, of x is equal to the exponent log base a of u. Well, log base a of x equals log base a of u. If that happens, if you have two logarithms with the same base equal to each other, then their arguments are equal to each other. Then x equals u. And if x equals u, ta-da, a raised to log base a of u equals u. So you can see that nothing cancels out. It's just a definition that's proven algebraically that a raised to log base a of u is u. Be careful though, because if I have a raised to the 2 log base a of u, that is not just u. That is equal to u squared. And that's because this 2 would have to become an exponent so that you have a coefficient of 1 in front of your logarithm. Okay, now that we've quickly reviewed our properties of logarithms, let's see if we can simplify, expand, and condense logarithms. We've got natural log of e raised to the square root of 2. We want to simplify that. First, the exponent is going to become a coefficient, square root of 2 times the natural log of e. The natural log of e is log base e of e, which is 1. The natural log of e is 1. The square root of 2 times 1 is the square root of 2. let's simplify e raised to the natural log of 3x. E raised to the natural log of 3x. Well, that's equal to 3x, and that's using our property. We want to expand natural log of 9 over 10. This is going to be our quotient rule. So we've got the natural log of 9. 9 is in the numerator, so that logarithm's positive, minus the natural log of 10, because 10 is in the denominator. Now, why does this work? Because the natural log of 9 divided by 10 is the same thing as 9 times 10 to the negative 1. So if I use the product rule, I'll have the natural log of 9 plus the natural log of 10 to the negative 1. And then 10 to the negative 1, that exponent comes out front, making your positive a negative, and you too will get natural log of 9 minus the natural log of 10. I like to just think of it, whatever factors are in the denominator of my argument, those logarithms are going to be negative logarithms. Okay, let's expand the natural log of the square root of x squared plus 1. First, we're going to rewrite the natural log of x squared plus 1 raised to the 1/2 power. And then our 1/2 power goes out front. And we'll have 1/2 times the natural log, and then absolutely must have parentheses around this argument. That is a must. Now we can't expand that any further because our argument is not a product. So we can't expand it any further because our argument is a sum, not a product. So let me come over here. See, we have a product here, not a sum. Therefore, products you can expand further, sums you may not. Okay, let's expand the natural log of xy over 5. And you can try these. You can press pause and you can try them and see if you've got it. And then come back and check your answer. The natural log of xy over 5 is the natural log of x plus, because y is in the numerator, it's going to be a positive logarithm, the natural log of y, and then 5 is in the denominator, so that will be a negative logarithm, natural log of 5. Okay, you try. I'm going to use highlighters. I'm going to highlight how many logarithms I should have. So I'm going to need 2 different colors here. X squared is a factor, and x plus 1 is a factor. This is going to be the product rule. So I'll have the natural log of x squared plus the natural log of x plus 1 in parentheses. And then one more thing I need to do is bring that exponent out to be a coefficient. 2 times the natural log of x plus the natural log of x plus 1. And x plus 1 must be in parentheses. In fact, you'll sometimes even see me just put the x in parentheses because I do tend to like to put parentheses around my argument when I'm writing logarithms. Okay. Let's go the opposite way and condense our logarithms. So here we have 2 terms. We're going to condense them to 1. So what I'm going to want to do first is I'm going to want to take care of this 2. So I'm going to have the natural log of x plus the natural log of y squared. These are both positive logarithms with the same base, so I can combine this to be the natural log, and then because they have positive logarithms, their arguments will be multiplied. They will be a product. So we tend to write xy squared just like that, xy squared. Okay, let's condense 2 times the natural log of x plus 2 minus 3 times the natural log of x. And you can try this one, see if you've got it. And if you're back with me, hopefully you're ready for an answer. I'm going to have the natural log of a fraction. We'll have x plus 2 quantity squared in the numerator, and then we'll have x cubed in the denominator. And now we're ready to solve. So let's solve a few of these. We want to solve e to the x equals 5. When your exponent has the variable, so when that variable is in the exponent, you're going to want to write in log form. That's how you get your variable out of the exponent. So this will be log base e of 5 equals x. And we know that log base e is the natural log of 5 equals x. The natural log of 5, well, that's just some numerical value. That's some numerical value that's between 1 and 2. It's between 1 and 2. Now, how do I know that the natural log of 5 is between 1 and 2? Is it because I've been doing this for that long, or did I actually go through a process to think about it? I actually went through a process to think about it. So I was thinking e raised to what power? Well, e raised to the 0 power is 1. E raised to the first power is about 2.718-ish. E raised to the second power is about 7.4-ish. That's about as far as I know that one, right? So where would 5 fit? 5 is going to fit between e to the first and e to the second. So I'm thinking it's somewhere between 1 and 2 for my exponent. And if we put this into our calculator, you can check it out. If you put it into your calculator, you'll see that x equals the natural log of 5, which is approximately 1.609. Now, that's what I tend to do, is write in log form. However, I think I've got some space over here. So let me come over here and use this space. You might have learned what teachers call natural log both sides. So I can pretend that these are arguments, e to the x equals 5, and I can go backwards and I can say, well, if e to the x equals 5, then the natural log of e to the x equals the natural log of 5. And if that's the case, then x can come out to be the coefficient times the natural log of e equals the natural log of 5. Well, the natural log of e is 1. X equals the natural log of 5. And that's what we got for an answer right here. X equals the natural log of 5. But when you can just go straight to writing in log form and not have to natural log both sides, I take the shorter route. Okay, let's solve another one. 10 plus e to the 0.1t equals 14. Okay, that was a nice break. We're going to isolate the term that has our variable. So I would subtract 10 from both sides. E to the 0.1t equals 4. And now I would write in log form, log base e, which is the natural log, of 4 is equal to 1/10 t. And 1/10 t, we're going to have to multiply both sides by 10. So I'd have 10 times the natural log of 4 is equal to t. And if I put that into my calculator, I get approximately, so I'm giving you a second to do that, 13.863-ish. If you got 13.863-ish, you did fantastic. Okay, now what do we do when we're solving and we have to solve for the argument? So now we have a logarithmic equation. Natural log of x equals 5. Well, just like we did over here, we took our exponential form and wrote it in log form. We're going to take our log form and write it in exponential form. So when the variable is in the argument, we're going to rewrite in exponential form. So e to the 5 equals x. Why e? Because this is a natural log, and the base of natural log is e. E to the 5 equals x. Done. Done, done, done. That's the exact answer. If I put this into my calculator, I will get an approximate answer. My answer makes sense because the argument has to be greater than 0, and e to the 5th power is definitely greater than 0. Okay, let's see if you can try the next one. Solve 3 plus 2 times the natural log of x equals 7. Okay, and if you're back, you're probably ready for an answer. I subtracted 3 from both sides. I got the natural log of x squared equals 7. Should not have done that. I did not get that. I got 2 times the natural log of x equals 4. I don't even know what I was thinking right there. Divide both sides by 2. The natural log of x equals 2. And then I got x equals e to the 2nd power. E to the 2nd power. Let me show you what I did here in red. I divided both sides by 2. So you can divide by the coefficient of your natural log. And then we'll box it and we call it a day. Now, had I done, let's just go back to what I was going to do. The natural log of x squared equals 4. Right? And then I was going to say e to the 4th equals x squared. But then I would have had to square root both sides, and I would have had a plus or minus. So x equals plus or minus e squared. How come that negative e squared was not an answer? How come x cannot equal negative e squared? Well, that's because your argument has to be greater than 0. And negative e squared would be negative. It would be less than 0, not greater than 0. Your argument has to be greater than 0. And anything less than 0 isn't going to work. So if you go the other route, you're going to have to think just a little bit further. It is a little bit easier to just divide out that coefficient rather than make it an exponent and falsely make it appear like there are more answers than there are. Okay, we got a few more things to work on. We need to work on doubling time. We need to work on tripling time. And we're going to work with just a couple of graphs to make sure that you can graph logarithms comfortably without too much stress.